Hello mathematicians, we're now going to take a look at the complex roots of unity. So the roots of unity are just the roots of 1, the things that multiply together, or to give us the solution of this equation, z to the n equals plus or minus 1. Now over the complex field, we'll discover that there are n of these roots. So for z to the n, there are n of these roots. And the roots are evenly spaced around a circle of radius 1. So they actually form the vertices of a regular n-sided polygon. Now that might sound a little bit like gobbledygook at the moment, but once we have a diagram in front of us, that won't be too bad. The reason that all the roots have a mod of 1 is because, given that they're on a unit circle, the mod of z to the n is the same as the mod of z raised to the n, which is 1. And they're all equally spaced, as you might have suspected from our earlier work when we looked at raising numbers to a power, because the successive difference in args will always be a constant value for a given case. So let's look first of all at the case for z to the n equals plus 1. So we're after the complex roots of plus 1. So if n is an even number, we know that there are two real roots. Plus 1 times plus 1 gives us plus 1, minus 1 times minus 1 gives us minus 1. So the other n minus 2 roots must be complex roots, and they always occur in complex conjugate pairs. Likewise, if n is an odd number, then there's only going to be one real root. So if we had z cubed equals plus 1, for example, our only real root could be plus 1. Z to the 5th equals plus 1, and so on. Minus 1 is not a possibility because that would change the sign. So there's only one real root, and the other n minus 1 roots will also be in complex conjugate pairs. So let's have a look at what this looks like in terms of our diagram, which might make a little bit more sense of our previous discussion about vertices of an n-sided polygon. Okay, so here we have, we want the roots of z to the n equals plus 1. And the first case we're going to take is when n equals 0. So n equals 0, obviously z to the 0 is plus 1. But when n equals 1, we've also got plus 1. So this, although this is numbered 0 here, sometimes it's numbered 1, so don't let that confuse you. The actual number down here is unimportant. The main thing we recognise is that when n equals 1, we have an odd numbered number of roots. We only have one root, which is plus 1. When n equals 2, then we have two real roots, 1 and minus 1. But when n goes to 3, we have three complex roots. So what number cubed gives you plus 1? Well, 1 does. But so do these two things here, which occur in complex conjugate pairs. You can see that z1 and z2 are conjugates of each other. They're in complex conjugate pairs because they have to multiply together to give us a real, because plus 1 is real. So they multiply together to give us a real, times this other real to give us our real answer of plus 1. They're all equally spaced because if we cube one of these, we've got to do the same thing to it 3 times. It's got to come back to being plus 1. And the spacing between them is 1 full revolution, which is 2 pi, divided by the number of roots, which is 3. Now we can make it look complex with this formula here, but all that this formula is really saying is that when we have n equals 3, then we're going to go up, change our values of k to 0, 1, up to n minus 1, 2k times pi on 3, so it's really saying we will have z0 equals 1, z1 equals cos 2 pi on 3 plus I sine 2 pi on 3, and then the next one around is 2 pi on 3 further, so that'll be 4 pi on 3, I sine 4 pi on 3, and that's it. They're our three roots. Now because they're equally spaced, and then remember they're all a distance of 1 because the mod of these complex numbers are 1, they're unity. So there's a unit circle, and because they're evenly spaced angularly, then it means the lengths of these sides will also always be even. So we form an equilateral triangle in the case of the three roots of unity. So these three roots of unity, sometimes called the complex cube roots of unity, we'll spend a little bit more time on. But let's keep going. So n equals 4. Our four roots are two reals, plus and minus 1, two other roots which occur in complex conjugate pairs, and because we need equal spacing between the four roots, then it has to be 90 degrees, so plus I and minus I are our other two roots, and clearly we form a square as the regular n-sided polygon. n equals 5, we go to a pentagon, and we see our roots here. So Z1 and Z4 in this numbering are the conjugate pairs, Z2 and Z3 are the conjugate pairs. If I multiply them all out, then Z1 times Z4 will give me a real, Z3 times Z2 will give me a real, times another real, which is Z0, and that gives me my real answer. And of course we've got a pentagon, hexagon, so the angle between any one of these is 2 pi divided by 6, which is pi on 3, n equals 7, and n equals 8, our regular octagon. So it's probably worth just looking at the fact that our pattern holds. When n is an odd number, we've got one real root, which is plus 1, and all the rest occur in conjugate pairs. When n is even, we've got one pair of, we've got two real roots, plus 1 and minus 1, and all the others occur in conjugate pairs. Now, if we look to take the complex roots of minus 1, then if n is odd, there's only one real root. So z to the 1 equals minus 1, obviously z equals minus 1. But if we had z cubed equals minus 1, then the only real root would be minus 1. So if n is an odd number, then the other n minus 1 roots are complex conjugate pairs, and if n is even, there are no real roots. So if n is an even number, like z squared equals minus 1, we know that there's a complex root, but there's no real root. There's no real numbers that can multiply together to give us a negative answer. So all of the roots are in complex conjugate pairs. So I guess we'll have a look at this in a moment, but I guess part of the challenge for you in this section is to codify this in your mind. What are the patterns when you want the complex roots of plus 1 and the complex roots of minus 1? So here we have z to the 1 equaling minus 1. Well, clearly our number is minus 1, which is signified by this vector here, length 1. When I go to n equals 2, then the square roots of minus 1 we know are going to be plus and minus I. n equals 3, we've got our three roots. Again, one of them is minus 1 and the other two form complex conjugate pairs. So you might again want to compare the pattern of this with the pattern that we got for z to the 3 equals plus 1. n equals 4, we get this pattern, and we won't go any further from that. So when we've got an even number, no real roots, and all the roots are in complex conjugate pairs, two pairs of complex conjugate pairs. So we'll have a look at some of these examples. So our first one is z cubed equals 1. So this is a sort of a special case where we work with what are called the complex cube roots of unity. So it says solve it algebraically and also by using the mod arg form. So let's look at it algebraically to begin with. And we could do this based on prelim algebra. So if z cubed equals 1, then that implies z cubed minus 1 is 0. We know the formula for the difference of cubes will give us that. So z equals plus 1 is one root, but then if we try to solve this quadratic, what we get is that we're going to have a negative under the square root sign, so that means that there are no more real roots. But we now know that we can write those as complex roots. So the two complex roots, the pair of roots which form conjugates, are minus 1 plus or minus I root 3 on 2. So these three roots are the three complex roots of unity. Now, even though 1 is a real number, all the real numbers are part of the complex domain. Now, let's have a look at doing it via mod arg form. So in mod arg form, we say, well, z cubed is 1 plus 0i, because that's what 1 is. So let z, which is the cube root, be cos theta plus I sine theta. So that when we cube z, this particular z here, so this is actually the more formal setting out of the taking the square root of a complex number. So, if we have that by De Moivre, z cubed must equal cos the 3 theta plus I sine 3 theta. Because the mod was 1, it's not that we're ignoring it, but it's always 1, so we don't bother writing it. So cos 3 theta plus I sine 3 theta equals 1 plus 0i. Now we could work with either part, but generally work with the real part. So that means by equating the reals that cos 3 theta equals 1, so theta equals 2 pi on 3. So that's the spacing. It's going to be the spacing of the roots on our diagram. We knew that anyhow. 2 pi divided by 3 is what we expected to get. So if we just go through and we put different successive values of 2 pi on 3 into this equation up here, we've got z1 is that. Now that will be the first root, which is given the name omega, and this is only special for cube roots of unity. Z2, which is this, becomes that when we apply our quadrant rules, and that is omega squared, because obviously if we squared this, we would by De Moivre multiply the 2 down and get 4 pi, so that's why that relationship holds, or that's one reason that relationship holds. And we can see that Z2 is the conjugate of Z1, and Z3, which is cos of 6 pi on 3 and sine of 6 pi on 3, simplifies down to 1, so that's our one real root. So our three roots are 1, going out here, cos of 2 pi on 3 and 4 pi on 3 going down here. I'll just smudge them all out. But if we joined all those up, then they're going to form, well, it doesn't look like it, the vertices of an equilateral triangle. So we have one real root, one pair of complex conjugate pairs. Now up here it says, notice that omega times omega squared, so this one times this one, is equal to omega cubed, which is 1, and also that 1 plus omega squared equals 0. Now, I'm going to just leave that till we discuss it in class for you to tell me why, but the little hint that I'll give you is to consider the sums and products of roots. I know we haven't yet done polynomials, but you know what that means for quadratics. Just do a logical extension of it. So we'll have a look at that in class. Now let's take a look at z to the 4 equals 1. So because this has an even number of roots, then what we will be expecting to get is 2 real roots and one other pair of roots as complex conjugate pairs. So for what it's worth, we'll look at De Moivre's theorem first. So if we let this be the fourth root, then z raised to the 4th power must be that, which equals 1 plus 0i, so a bit haywire there. So equating reals, cos to the 4th theta equals 1, which means that theta equals 0, pi on 2, 3 pi on 2, 2 pi. I sort of assumed that you're good with this part here. Remember that what this means, that we take the possible values of cos of 4 theta equals 1. We're going to be looking just over the domain 0 to 2 pi, so we have to change this to 0 to 8 pi, solve it, and then divide through by 4, so as per the prelim unit. Now, when we take those values of 0, pi on 2 pi, 3 pi on 2, and 2 pi, and put them into this, then these are the 4 roots that we get. We expect to get 4 roots. Now, algebraically, similarly to before, z to the 4th equals 1 implies this, which gives us this. First bit's okay, difference of squares. The second bit we can do, now that we have complex numbers, also as a difference of squares, and we get the same 4 roots. It's probably quicker algebraically than in mod arg form here. What does our diagram look like? Well, out here we've got our 2 real roots, and here we've got our pair of complex conjugate roots, so they form the vertices of a square. And the angle between all those roots is 90 degrees, as shown in here. Now finally, for z to the 4th equals -1. So we know that this is an even power. There are no real roots because there's no power we can raise, no even power we can raise a real number to get a negative answer. So we expect to get 4 complex roots in complex conjugate pairs. But our methodology is the same. So if this is what one root is, then if we raise it to the 4th, that will be our set of roots. Equating the reals, we get this, which gives us the values of theta as these ones. And so we go through and plug those in to get our z1, 2, 3, which we see is the same as the conjugate of z2, 4, which we see is the same as the conjugate of z1. So these are our 4 roots, and again, the 4 roots are placed 2 pi on 4, so 90 degrees apart, pi on 2 apart, but because there are no real roots, the first one is offset by pi on 4, and then they go round in the circle after that. So, have a go at the questions on this, which are the remainder of set 4 class.